Hello and welcome back. In today's video we will talk about optimization. Optimization is extremely useful because all engineering problems can be formulated as optimization problems. Of course, here we are interested in control, so we will see how optimization can be applied to formulate and solve control problems. So we will be talking about optimal control. This is where optimization and control meet. I mentioned that all engineering problems can be formulated as optimization problems. I should also say that in the majority of cases, it is a good idea to do so, right? To formulate problems in general as optimization problems. Indeed, control problems are optimization problems often. I mean, you can state control objectives as an optimization problem. You can state a learning objective as an optimization problem, and this is what people do in machine learning. You can formulate an estimation, a parameter estimation objective as an optimization problem, and so on and so forth. I'll give a few examples related to control in the following slides. So this is how this will work today. First of all, I will define what optimal control is, but I will not tell you how to solve it. So I will just try to motivate why we are interested in solving such problems. Then the focus will be on optimization, and then we'll come back to optimal control, and we will solve perhaps the simplest problem, the simplest optimal control problem, which is the discrete time, finite horizon, linear-quadratic optimal control problem. Again, it's a lengthy title, but there is no short version. Right, so we will be focusing today on convex optimization. And let's start with optimal control. So what is optimal control, more or less? How can we describe it? It is controlling a system, trying to steer a dynamical system to a certain target, to a certain destination or set point, while we minimize a certain performance index. So we have a way to measure and characterize the performance of trajectories of the system, and we want to optimize it, to minimize it, for example. And we will do so over a finite or infinite period of time, and taking into account any constraints that might be acting on the system states and inputs. For example, you might have limited actuation capacity. When you drive a car, it doesn't make sense to drive the car by steering the steering wheel too much. There are certain limits. If you have a pipe and there is, for example, water running through it, then you can turn the valve to the closed position, which corresponds to a 0% flow, or you can turn it all the way to 100%. So your actuator there, the valve, can only take values between 0 and 100%. You cannot use the valve to make the water flow at 120% of the maximum, or go negative, or have a negative flow. Or, for example, if you have a switch, then the switch has only two possible values. It can be on or it can be off. If on is 1 and off is 0, so these are the two only values that you're allowed to, that the actuator is allowed to have, your control action is allowed to have. So these are examples of constraints. You can have safety limits. If we are talking about autonomous vehicles, then a safety limit is that the car drives between the boundaries of your lane only. Or if we're talking about a chemical reactor, perhaps, then a safety limit can be that there is a minimum and a maximum temperature. Other considerations are the economic operation of whatever we are controlling. For instance, back to the example with a vehicle, economic operation corresponds to minimization of fuel consumption, or if you're operating an electric device, minimization of electricity, of power consumption in general, or at the same time, maximization of productivity. and these objectives can be conflicting, so you cannot have minimum consumption of fuel and at the same time maximum productivity. You need to strike a desirable balance between these two. So these are examples of objectives we can have in optimal control. To put it concisely, you have a dynamical system. Think of a vehicle that needs to drive from an initial position to a final destination, to a final position. The question is, how can you do that in a finite time so that you minimize a certain performance index, and at the same time you take into account any limitations you might have, either limitations on actuation, on inputs, on control actions, or safety limitations on the states, on the state variables of your system. There are many applications of optimal control. One of the first applications was chess, the game chess and checkers, studied by Richard Bellman in 1965. Also, how to reach the moon with minimum fuel consumption. These problems were studied in the 60s and 70s. And then we have inventory control, autonomous trains, car parking, robots are operated primarily with optimal control. Then you have even systems that you wouldn't really think of as engineering systems, like in macroeconomics, how to maximize the GDP of a country, or how to minimize unemployment, or do both at the same time. And then we have model predictive control, which is the main objective of this module. So actually we are studying optimal control because later we will use it to design appropriate model predictive controllers. Now let's try to be a little more technical when it comes to this form of optimal control. This is one of the simplest possible formulations of optimal control problems, the linear-quadratic optimal control, and it is in fact one of the very few cases that we can solve on paper. In principle, we cannot solve optimal control problems analytically on paper. We have to use software. This one is an exception. So this one is a case that we can actually solve ourselves without computers. And imagine that you have a system whose state starts here. This is at time 0. This is your state. This can be, for example, the position of a vehicle. And this is a certain target, this point. This is x1, this is x2. Imagine that this is just you looking at it from the top. So imagine you exercise a control action, and the system from here goes here. And then another control action, and from here the system goes here. You will see that x1 is a function f0 of x0 u0. This is the system dynamics. So some dynamics, for example, some equation that comes from physics, I don't know, like Newton's laws of motion, that dictate and explain how, if you apply a certain action, you apply a certain force, for example, imagine that u0 can be a force, how the system moves from this initial position to this position at time 1, and then to this position at time 2. So what happens is that you apply an action u0, the system goes here, then you apply an action u1, and at the next time instant the system goes here. I should have mentioned that here we study the system in the discrete time domain. So we have the 0th or initial time, t equals 0, then we have t equals 1, t equals 2. So t is an index. It is not a continuous time variable. So now imagine that the system starts from here, you apply the control action u0, the system goes to x1, then you apply the control action u1, the system goes to x2, you apply the control action u2, the system goes to x3. And needless to say, had you applied a different sequence of actions, like a different u0, the system would go here, then perhaps here, and so on. So by applying different sequences of control actions, you can make the system move in different ways. Now, the system is at an initial position x0, and you apply a control action u0. To apply this control action, you have to pay a cost. Imagine if you're driving a vehicle, this cost can be nothing else but the cost of fuel. So if you step down on the pedal, the accelerator pedal, this cost will be high. If you take it slower and smoother, this will be a lower cost. So there can be a cost associated with fuel consumption, but the cost here, this cost function L of x0 u0, should not only reflect how much you pay to control the system, to operate the system, it should also reflect your control objectives. And here the control objective is to reach this target. So it makes sense to choose L to be equal to something like the fuel consumption plus some additional cost that has to do with the satisfaction of the objective, which is to reach the target. So a cost for not reaching the target, which, if you think about it, that's a synonym for the distance to the target. So here's how it goes. You start at this x0, you start at this position x0, and you have to make a choice there. Either you will consume lots of fuel, but you will go very close to your destination. So this red line here, this red arrow, corresponds to lots of fuel, but you go closer to your target. So this is one possibility. Another possibility is to do something like this. So this is the eco-friendly operation. So you don't go that close to the target, you move slower, and after one time instant you're not that close to the target, but you have consumed less fuel. So here is the dilemma that the controller has to address. Either it will go very fast, it will consume lots of fuel, but it will reach the target fast, or it will take it easier. But this anyway is reflected by this cost function. And you can say that fuel consumption for me is really important. So you can do 1000 times the fuel consumption plus the distance to the target. Or you can say, I don't care about the environment. I will do 1000 times the distance to the target, and I will penalize again the fuel consumption, but it's not so important for me. So this is where the designer needs to make a decision about how the system will be operated, how aggressive or how smooth it will be. But the thing is that we start the statement of the control problem by defining this function L, and this is a function L of the state and the input, and this is called a cost function. In fact, we call it the stage cost. And let me move on to the next slide. So at every time you have a different cost that you have to pay. So we said that at the beginning you are at x0, you take a decision u0, and then you have to pay L of x0 u0. Then at time 1 you are at x1, you will make a decision u1, and you have to pay a cost L of x1 u1. And at time 2 you are here at this point, you will make a decision u2, and the cost you have to pay is L2 of x2 u2. So at every time instant, based on where you are and based on what you will do at this point, you have to pay a corresponding cost, which once again reflects the fuel consumption or the actuation intensity, and on the other hand, the attainment of the target, how close you are to the final destination. At the end, you have to stop at a point. You have to stop because this is what we call a finite horizon, a finite horizon problem. So you say, I'm studying this system for 10 steps only, as opposed to an infinite horizon problem, which we will talk about briefly a lot later. At the final time, x3 here, so at time 3, you say, I have to pay now a final penalty, a final cost, that penalizes only how far I am from the destination. So there is no other decision for you to make. The time is up, you can't make any more decisions, but then you have to judge how this whole sequence of decisions you had made already, like U0, U1, U2, and that's it, you can't make any more decisions. So you have to evaluate at the end how close to the target you found yourself. And if you put everything together now, the initial cost at time 0, the cost you had to pay at time 1, the cost you had to pay at time 2, and the terminal cost, this is called, let me write it down, this is called the terminal cost function, then you have what is called the total cost function. The total cost function is the summation of all costs. So it is this cost plus this cost plus this one plus the terminal one. It is the, check this out, the summation from time 0 to time 1 and then 2 of the stage costs plus the terminal cost VF. And this is what you have to pay. So now the thing is that let me make a copy of this sketch on the right. So let's say that you make a different, you apply a different sequence of control actions. This is the original one. And you decide to take entirely different control actions. You try to be more aggressive. You try to go here, and then here, and then here. So it looks like you made a big stride with U0, and then U1, and then U2. This entails a certain cost. So if you would like us to write this down in pounds, let's say that this trajectory here is a trajectory for which you have to pay 10 pounds. And let's say that this trajectory is one for which you have to pay 20 pounds. So which one is better? The first one, the cyan one. So this trajectory is better because it leads to a lower cost. So what is key here is how you will define this cost function. Different cost functions lead to different best behaviors. So what you define as best is somewhat subjective. The ingredients now of what we just described, let's do a little summary. The ingredients of a finite horizon, a discrete time finite horizon optimal control problem are the following. First of all, you need a system. You need a system. You need to know what you're talking about. Is it a car? Is it a plane? Is it a nuclear reactor? What is it? So the first thing is a dynamical model of the system. What is it governed by? Is it Newton's equations of motion? Is it Kirchhoff's laws of a circuit? Is it heat exchange? Is it a heating system? What is it exactly? And the equations that we have to talk about dynamical systems have this form. They say the state of my system, denoted by x, at the next time instant, at time t plus 1, is some function f, it depends on the problem of course, of my state at the current time and the control action at the current time. The second thing you need is a performance indicator, a cost function to be minimized. So what is this cost function we are using in discrete time finite horizon optimal control? It is a summation of these functions called LXTUT plus VF of x at the terminal, the final time. Let's call it xn, n being the final time, or the prediction horizon. N is the prediction horizon. The third thing you need is to be able to measure the state of the system, to be able to measure the initial state, to know where you are actually. So we say we start from here, we assume we know that. It is a very simple assumption, but we still have to state it. It means you have a sensor, you have a way to measure, to see that your car is here, that this is the temperature at the current time of your room. If you have an air conditioning system, you need to be able to measure the state. If you're not able to measure the state, that's probably fine, often, so long as you can somehow estimate it. And the last thing you need is any constraints, any safety considerations, or any other types of constraints that we have. Now, unlike PID, because it is very natural to ask, we know about PID control. PID is very famous and very widely used in the industry and in many applications. What is the difference between PID and this optimal control? Several things. For one, PID is not optimal in a certain sense. I mean, although you can tune it absolutely fine, you can have absolutely fine PID controllers, still there is no notion of optimality. So this is a plus of optimal control. Second, and that's the most important, is that a PID controller cannot take into account constraints. So in optimal control, if you tell the controller that this maximum value should be respected, that the temperature should not exceed this maximum value, the optimal controller will take care so that you don't have any explosions. With PID, unfortunately, you cannot do that. The third thing, which is also very, very important, is that with a PID controller, you can only control a system that has one output and one input. You can control one thing using one thing. In the example of the vehicle, you have several control actions. You have the steering wheel, the steering angle, and you have the acceleration reference from the pedal, and you have the brakes as well. So you have lots of control actions involved in this example. And you have lots of states. You have the X position, you have the Y position, and you have the orientation or heading of the vehicle. So you have three things you need to control. The PID doesn't seem to be a good idea in this example. So this is why this is a motivation for looking into optimal control. And in many engineering applications, optimal control is exactly what you need. Now let's move on with the formulation of the problem. It goes like this: starting from an initial state x0, I know where I'm starting from, and applying a sequence of inputs u. Please pay attention here. This is a u boldface. When we write it on paper, we will be writing it like this, because it's impossible to do a boldface u on paper. We do un, and we underline it. So when you see u boldface n, subscript n, when we write it ourselves on paper, we will be using the notation un underlined. Back to our discussion about optimal control now. So starting from an initial state x0 and applying a sequence of inputs u boldface n, we obtain a sequence of states, right? And we can measure how well we did by that choice of an optimal choice of a sequence of inputs by measuring the total cost we have to pay, the total cost that is associated with this choice of control actions that leads to this sequence of states. So we measure how good this is, how costly this is. This L is the stage cost function, and this VF is the terminal cost function. You must have observed here that it is L underscore T. This simply means that I can be measuring my cost in a different way at different times, but in principle this can be just L. Often it is just L instead of L that changes with time. One special case of optimal control, what I just showed you was the most general case, but now one special case that we focus on a lot is the case where the system is linear. It is xt plus 1, it is not some fancy function f, but it is just a, x plus b, u. Matrix, a given constant matrix a times the state plus b times the input. So all you need to know the system dynamics, all you need to know is a pair of matrices A and B. Again, in this equation I have A that depends on time and B that depends on time, but of course a simpler case is to say xt plus 1 is equal to axt plus b ut. The system is perfectly and fully characterized by two matrices, A and B. Once again, x is the state of the system, the state, and u is the input. And of course, needless to say, nothing prevents the state and the input from being vectors. They don't need to be just numbers, scalars. They can be vectors. This can be a vector of Rn. This can be a vector of, say, Rm. Ut depends on time, xt depends on time. So starting from, I'll repeat what I said in the previous slide, starting from an initial given state x0 that I know I can measure, if we apply the sequence of control actions u boldface n, a sequence u0, u1, u2 up to un minus 1, we will obtain a sequence of states xn, x0, x1 up to xn. And we define the total cost function exactly the same way as before. But now I am using a particular form for my function L, a convenient form for my function L of x comma u, this function over here, which is 1/2 times x transpose qx plus u transpose ru. This is an interesting choice of function. You might be already familiar with the expression x transpose qx and u transpose ru. These are quadratic forms. Which we studied in the introductory lectures on linear algebra. Now I will delete x transpose qx and I will simply write norm of x squared with the matrix Q, because the norm will allow me to understand better what this term is and what it does, plus u squared norm with matrix R. The norm measures how far my x is from 0. It measures how big my vector x is. So this thing here, norm of x squared, is a metric, it's a measure of the length of how big my state is, or how far away from the target is if the target is 0. And this measures how big my control action is, so how far away from 0 it is. So we can relate this term with fuel consumption. You can think of it like this, fuel consumption. And this term, the first term, has to do with the distance from the target. This is the first term is the distance from the target, if the target is 0, and the second term is my fuel consumption. The higher the u, okay, u is a vector, but the higher the norm of u, the more fuel, so to speak, we need to consume, the more effort we need to put to control the system. the fuel consumption, or if you prefer the term, you can call it control effort. So let's go back to the cost function. The cost function, this one, is a summation of the stage cost function plus a terminal cost function. This is the terminal cost that measures how far away my terminal state, my state at time n, is from 0, if 0 is the target. So this quantity here is the same as 1/2 norm of the terminal state squared, but with a different matrix, PF. PF, F as in final. And if we look at the whole thing, this is the problem of the total cost function is a sum of stage cost functions plus the terminal cost function. Now you must be wondering, what are these matrices Q, R, and PF? These matrices are in principle positive semi-definite matrices. Q is positive semi-definite, R is positive definite, and PF is positive definite as well. And they have different dimensions, so Q is n by n because it penalizes the state, which is of dimension n. PF is of dimension n by n, which again penalizes the state. And this matrix R is m by m, same dimension as the input, because this applied to penalize the input. Let's try to make sense of what these matrices might look like, some particular examples. So the easiest choice for matrix Q, for instance, is to take it to be the identity. What happens if you take it to be the identity? Then the quadratic form x transpose qx becomes simply x transpose x, which is nothing but the Euclidean norm of x. So this is what happens if you use the identity matrix. Let's see now what happens if you use a simple matrix. And a very simple form of a matrix is a diagonal matrix. So you can put some numbers here, and all the rest entries, the other entries, are 0. So what happens then is that x transpose qx looks like this. q11 times x1 squared. This is the first entry of the vector x. q22 times x2 squared. This is the second element of the vector xt, and so on and so forth. qnn, this is the last entry, times xtn squared. This is the last entry of the vector x. The vector x is like this. xt, x at time t, is a vector that has coordinates 1, 2, down to n. Because, as we said, the state of the system can be a vector. You can have a system that has as a state, like the position of a vehicle, the velocity of a vehicle, the heading of a vehicle, and these are different entries in a vector. And you might want to penalize them with different weights, to give different importance to different variables. So you might say that I don't care about the velocity. Let's say that this is the velocity. This is the position. You can say, I don't care about the velocity. If it is high, for example, I don't care. Let it be high. So I will put a small penalty on the velocity. But I care about the position. I don't want the position to be high, as in far away from the target. So I will penalize this a lot. I will put a big number here. Or you can say, I'd rather be safe. So I will put a small penalty on the position, and I will put a high penalty on the velocity. I will choose q22 to be high, because I don't want the velocity to be very high, right? Of course, if there is a limit, as in a, for instance, legal limit, you should impose a constraint, but we'll discuss about this later. But what I wanted to say is that this is what you can do with matrix Q. You can take it to be a diagonal matrix, and now these numbers are the importance you give to the different elements inside your state. And likewise, you can take R to be a diagonal matrix to give different importance to different control actions. And if you put everything together, you end up with an optimization problem. The optimization problem looks like this, like what we have here. It says, given the initial state, we need to solve the following optimization problem. First of all, not to have any misunderstanding, what you see here is simply the name of the problem. We call it Pn so that we don't have to say the above optimization problem. So now we give it a name so we can refer to it. This is not an equation or anything. This part is just how you call the problem. We call it Pn. And we are trying to minimize the total cost function. We are trying to minimize it and determine the sequence of control actions and the corresponding sequence of states. This is what we are looking for. Subject to, meaning taking into account the system dynamics. And of course the fact that we know where the initial state is. So we say that the initial state x at time 0 is equal to a given position x. That's it, really. So this is what we are trying to solve, and the most important observation here is that this is an optimization problem. So we will dedicate the remaining part of this lecture to defining actually a little more properly what an optimization problem is and how can we solve optimization problems. Once you solve this problem, so say you have solved it somehow either by yourselves on paper or using software, we determine a sequence of control actions. A sequence of control actions that we denote by U boldface subscript n. And this sequence that we determine minimizes the total cost function Vn given the initial state x naught. This problem that you see here on this slide, this problem, is the famous discrete time, finite horizon, linear-quadratic, optimal control problem, provided of course that this function Vn here is the function I showed you previously, namely this function over here. This function. This function is a quadratic function. And this equation is linear in x and u. So this is linear. And this is why we say that we have a linear, quadratic, optimal control problem. We say it is finite horizon because this is a finite number. It doesn't go from 0 to infinity. Finite horizon, linear, quadratic, optimal control problem, and this is the optimal control problem. The questions we ask here are, what is a solution really? What is the definition of a solution, of a minimizer? What is the meaning of the word minimizer? It's not a difficult question, but still it's a question we need to ask. Does a minimizer exist? Is there a solution of this problem? If it exists, is it unique, or can I find another one perhaps? And how can, of course, that's the question that most people are mostly interested in, how can we compute such a minimizer? And these are questions that will be answered after we have a look at optimization. So this is the next section of this lecture, convex optimization, but I think I will stop the recording now and come back with to make a second separate video on convex optimization. For now, thanks very much for watching, and I'll see you again. Bye.